So in addition to whatever we have learned in PN junction diode, this is a special area which we need to go through. I'm just giving you some basics of this. Right. Please try to understand when I am writing NE. Here I am representing NE refers to number of electrons per unit volume. Similarly, when I am writing NH, I am representing number of holes per unit volume. Right. Now, what is happening over here? So, they are related as Ni square. They are related as Ni square. Where, and this is called, this equation is what we will call as mass action law. Here, Ni refers to carrier concentration. Remember, it is a function of temperature and it depends on the energy gap also. For a pure intrinsic semiconductor, for a pure intrinsic semiconductor, Ne is, NH is equal to Ni. As I mentioned, Ni is a function of temperature. As per higher order studies, I can take this relation from standard books as this is equal to e to the power of minus delta Eg, energy gap, by 2 kT. It is purely a function of temperature, or in other words, at a given temperature, it depends on delta Eg, energy gap. In fact, by increasing the temperature, I am increasing Ni. And hence, that is the reason why a semiconductor will have a negative temperature coefficient of resistance. Because as temperature increases, resistance decreases, resistivity decreases. Also, energy gap is also a function of temperature. For example, energy gap in case of silicon can be written as 1.21 minus 3.60 into 10 power minus 4. T means temperature in Kelvin. Similarly, energy gap in case of germanium is 0.785 minus 2.23 into 10 power minus 4 Tesla. Remember, none of these things were there in NCERT, so don't worry, they won't ask you this. I'm giving you some additional information. Now, till now, this is all pure material, pure intrinsic semiconductor. Now, you are doping. When doping is available, then the study starts differently. For this purpose, I am using new terminology, ND. Here, ND represents number of donor impurity. Na represents number of acceptor impurity. Remember, when I am defining both are defined in ionized state. Don't get confused. Suppose you have added a p-type material, which means uh, I am discussing about the acceptor concept only when it accepts. Earlier, it is a neutral. Even though you have done doping, everything is neutral. When will that doped material gets charged? When it accepts or rejects? Sorry, accepts or donates. Don't say reject, donates. Right. And NH, number of holes intrinsically generated. And Ne stands for number of electrons intrinsically generated. Unfortunately, no such discussion took place in NCRT. But what if they cross the limits? And that is the reason why I am here. So now, according to conservation of charge. What is total positive charge? When I donate, the impurity becomes positive. Holes anyway positive. So therefore, Nd plus NH is a total positive quantity. This should be when I accept p-type impurity, when it accepts, become negatively charged. Electron being negatively charged. So therefore, N acceptor plus N E. Remember, law of conservation of charge and law of what do you call mass action. These two will decide the fate of any numerical. You must know these two to solve any numerical related to p-n junction persons. Now, see again, if I study this differently, as let us purely focus on p-type material. If I am speaking purely about a p-type material, or p-type material refers to what? Don't get confused. P-type material refers to, in p-type there is only acceptor, it won't donate. Therefore, Nd is almost zero. And whatever the holes, that is almost same as A acceptance. Because N hole much greater than N electrons. And therefore, for mass action law, I can say that Ne is, don't get confused with this part. Na plus Ne almost becomes Na. So therefore, from this I can say Ne is Ni square by Na. I'm not cheating you. You said NH, Ne is Ni square. So number of electrons calculation can be done in a p-type material according to this. P-type material basically are acceptors. So number of minority electrons is minority in that. So now how to remember this equation? Minority is carrier concentration square by Adukune batch. Acceptors. Minority is carrier concentration square divided by Becquerel's acceptance. Now, on the other hand, in N-type material, so what can I observe here in an N-type material is N-type means donates. There is no acceptor. So therefore, N acceptor is almost 0. Now, N D plus N whole is equal to Ne. Equation will change. So automatically Ne is N, and by the way, hello, ఇక్కడ కూడా అదే చేశాను నేను యాక్చువల్గా. N type, NH very small when compared to Ne. So therefore, almost N donor is the same as Ne. So therefore, N whole minority in N type is Ni square by N donor. So what is now every time, please try to remember how to remember these formulas. I am giving this equation to find minority all the time. So minority charges is carrier concentration square divided by either donor or acceptor. In case of N-type material, N-type material holes are minorities. So NH is carrier concentration square divided by N-type contains donors. P-type material, electrons are minority carriers. So minority is carrier concentration square by what is P-type material basically? Acceptors. Adi gurtu pettukunte antaru. You will get questions on the basis of this. So I'll try to give you a rough idea what nature of questions you will get, so that we can basically focus on these areas properly. So I'll take one by one. Now please go through this question carefully. Everyone, please go through these questions carefully. See, I am expecting questions of this type. A semiconductor has equal electron atom hole concentration of 6 into 10 power 8. So basically, initially it is intrinsic. On doping with certain impurity, electron concentration increases to 9 into 10 to the power of 12 m per meter cube. Identify the new semiconductor obtained after doping. Obviously, this is Ne is greater than N whole. So therefore, what type of conductor this is? N type. Done. Calculate the new hole concentration. Simple. Number of holes is equal to Ni square by, this is donor. Donor or not? Yes, donor. So Ni square, what is Ni square? 6 into 10 to the power of 8 whole square. That's what given by you initially. And this is N donor, 9 into 10 to the power of 12. So finally, what is that you are getting is 36 by 9, 4, 16 minus 12, 10 power 4 per meter cube. Obviously, it is of the order of 10 power 4 and E is of the order of 10 power 12. Come on, man. That is true. Right. Next. How does the energy gap vary with the doping? See, usually, what is the objective of doping? Doping purpose is to reduce the energy gap. So just because of doping, the energy gap, what is happening? Decreases. Right. What a simple question is. Right. I'll add one more question. Let me add one more question. And this is a jumbo question. Please work on this. Meanwhile, I'll add one more. Actually, I planned only two questions. That's all. Right. This one also. After this, I'll add one more. With these questions, we're almost covering the planned content. Right. Please make sure that you take care of this question. Germanium specimen is doped with aluminum. The concentration of acceptor. By the way, what is aluminum? What type of doping finally it is going to be? No confusion. Already I have given this information earlier to you. Here is that information. Here is that information. I've given information earlier. What are impurities? What type of impurities you can here? Boron, aluminum, indium, gallium. This makes p-type metal. Given clearly, no? Boron, trivalent impurity. Boron, aluminum, indium, and gallium. So that makes p-type impurity. But by the way, what is our question? Aluminum. So what type of impurity is? Trivalent impurity. So this is purely a trivalent impurity. So therefore, okay, no issues. The concentration of acceptor atoms is nearly. Okay, no issues. That is 10 power. N acceptor is 10 power 21 per meter cube. Intrinsic carrier concentration, Ni, is 10 to the power of 19. Ne is what they're asking. Tell me the formula. Ne, minority, is Ni square plus Na. So this is 10 power 19 into 10 power 19 by I acceptor 10 power 21. This will become 10 power 17 per meter cube. Still 10 power 17 and 10 power 21. Almost a difference of 10 power 4. So you can neglect, no issues. Are 1001. Almost you will neglect. Right. 10 power 4, not 1000. 10,001. Any doubts? One simple substitution. Next. Yes. With this, I think I can close. In a pure germanium sample taken at a temperature of 300 Kelvin, concentration of electron hole pairs is 7 into 10 power 5 per centimeter cube. So what that's they have given? Ni is given as 7 into 10 to the power of 15. Right. If one antimony atom is doped into germanium for 10 power 7 germanium atoms. By the way, what is antimony? Can you please help me in writing this? So therefore, impurity added is pentavalent. So now what type of content will be there? Donor. I will have donor impurity. Right. Now, yeah, by the way, the number density of germanium atoms is given 5 into 10 to the power of 28. Can you please help me? What is ND here? ND. Are you said 1 for every 10 power 7 germanium. So now you have 5 into 10 power 28. So what is that I need to do? 5 into 10 to the power of 28 divided by 1 into 10 to the power of 7. This works around 5 into 10 to the power of 21 centimeter cube. Any doubts? అదే ఇక్కడ సెంటీమీటర్ క్యూబ్ ఇచ్చారు కదా కాబట్టి అంటే ఇది సెంటీమీటర్ క్యూబే అయి ఉంటుందని తీసుకోవాలా ఓకే కింద మీటర్ క్యూబ్ ఇచ్చారు కాబట్టి అలానే పోదాం మనది ఏం పోయింది విల్ గో విత్ మీటర్ క్యూబ్ ఓన్లీ నో ఇష్యూస్ ఓకే ఫైన్ what is that you want? Calculate the factor by which number of charge carriers increases due to doping. What type it is? Pentavalent. What you will have? Donors. So what are minorities? Holes. ND. So what about the number of holes? Holes. Number of holes. Number of holes. Calculate the factor by which, okay, germanium atom, half of the impurity atom, my goodness, half of the impurity atoms contribute electrons to conduction band. So you should not take this. Again, you should do by 2 also again, by 2. 2.5 into 10 to the power of 21 per meter cube. Right. And all this is nothing but number of electrons per unit volume. By the way, what is your question? Factor. Factor by which it is changing. Right. Who cares for holes? That is electron. Okay. New number of electrons per unit volume. Initially, what was the number? Initially, the number concentration of electron hole pairs. I have done one mistake. Electron and hole pairs means carrier concentration. Electron and hole pair contribution in a pure is total number density of the charges. Total charge density initially is number of holes plus number of electrons. That is the number of charge. That will become 2 times 7 into 10 to the power of 15. 14 into 10 to the power of 15. Final charge density, please. Final charge density. God said, don't please add Ne plus NH. Why? Negligible. Negligible. అరే ఏంటో హోల్స్ క్యాలిక్యులేట్ చేద్దాం నిజంగా ఉందా నీకు బాలాజీ? చూస్తున్నాం కదా 10⁴ ఉంటుంది. యాడ్ చేసినా డెసిమల్ తర్వాత ఫోర్త్ ప్లేస్ తర్వాత వస్తుంది. సో యూ డోంట్ రిక్వైర్ దట్. Therefore, final charge density is almost nearly Ne dash, which is nothing but 2.5 into 10⁻21 per meter cube. Right. So this is a mistake. It should be meter cube only because they cannot give two different units. Now, fraction is Ne dash minus 14 into 10⁻15 divided by 14 into 10⁻15. Not tell me. 10⁻21 term minus 10⁻15 term, will that makes any sense? No. So this is nearly 2.5 into 10 to the power of 21 by 14 into 10 to the power of 15. That works nearly 2.5 by 14, nearly 1.8 into 10 to the power of 20 తీసుకోండి ఎక్కడ 15, 10 to the power of 5. Very big fraction. Very big number. Now, have you understood why doping is done? Why doping is done? This is the reason. Before doping and after doping, the factor increased by a lakh times. That is why doping is done. Okay, that's all right. I just want to tell you only these three things. And I have already posted these notes to you. But एक minute, just एक minute. Have you all studied these diodes, full wave rectifier, half wave rectifier also? Full wave rectifier, half wave rectifier, full wave rectifier and half wave rectifier, bridge rectifier, bridge rectifier. Only these things you need to go through actually. But very less chances are there getting questions from this. But NCERT, there is a special case, filter circuit. You will apply AC and you will draw the output through a capacitor. Why output is drawn through a capacitor? The reason is clearly explained here. To get steady DC output from the pulsated voltage, normally a capacitor is connected across the output terminals parallel to the load resistance. One can also use an inductor, of course. Always to separate AC from DC, you have two options, capacitor as well as inductor. But in this case, we prefer capacitor. These are called filter circuits actually. So why capacitor is used? Right. Now, while charging is happening during this process, remember, during this process, capacitor gets charged. But during the time when pulsating voltage is decreasing, capacitor gets discharged. But the discharge rate of capacitor and falling rate of the input is different. Now what happens is that it will slowly fall down. Meanwhile, again, there will be top up. Now, after some stage, what happens is output, this is taken care, and again this is taken care, and again this is taken care. This is how you'll get the output. It is I'm reducing some pulse. So therefore, that is what mentioned here clearly. Across the capacitor is rising, it gets charged. If there is no external load, it remains charged to the peak voltage of the rectified voltage. When there is a load, it gets discharged through the load and the voltage across it begins to fall. In the next half cycle of the rectified output, it again gets charged to the peak value. So likewise, the process gets repeated. So we will select the circuit having a time constant, whereas a larger value of R is used in the RC circuit. Or larger value of C, if I am using larger value of R, power loss is high. If I use a larger value of C, less power loss, more time constant. That is how I can rectify the voltage output. So such a rectifier uses capacitor as a filter circuit. This entire highlighted area is very important. So why we use larger capacitors? I have given the reason. NCERT, this is what they have mentioned. This is one important aspect which you need to remember.